All right, welcome everyone to this week Autonomy Talks. This week is a great pleasure to have Professor Amanda Prorok, who is an associate professor in the Department of Computer Science and Technology at the University of Cambridge in the United Kingdom. Something about Amanda, so she actually completed the PhD at EPFL here in Switzerland. So that's a funny comeback, where, by the way, she also obtained the ABB Award for the best thesis. After that, she moved to US, where she joined for a postdoc, the GRASP lab at the University of Pennsylvania. And then she joined Cambridge. So her research lies in the field of multi-robot and multi-agent systems. And in particular, she's interested in finding algorithmic solutions for hard coordination problems. And the typical applications are robotic warehouses, intelligent transport, and cooperative robot swarms. For her work, she has been awarded various grants and awards that I have listed in the bio, maybe among the most important, the ERC Starting Grant and the Amazon Research Award. Today, she's going to talk about learning communication for decentralized coordination in multi-robot systems. And since this touches many of the topics we're interested in our group and in this community, we are very happy to hear what she's going to talk about. So Amanda, go ahead, the stage is yours.
Thank you very much, Joy, for the very kind introduction, and also thank you very much for the invitation to speak at this seminar series. It's a pleasure. So today I'll be presenting work that has been done in collaboration with some of my students and some of my postdocs. So their names are listed here, and I'll also be referencing to all the publications that we put out jointly. So without further ado, I'd like to kick off by just giving an introduction to what it is that we do in my lab and what the vision is. So we are really driven by this idea that the next wave of computing is about the convergence of ubiquitous computation, communication, and artificial intelligence. And this is also backed up by many of these think tank predictions that say that within the next 20 years or so, over 1 trillion devices will be connected, and these are intelligent devices. Okay? And so what we are saying, or what our research is all about, is that communication enabling processes to coordinate is good, but it's not enough, because it's really about the decisions that this communication triggers. And with this context in mind, what my lab's mission is about is to develop the techniques that endow the autonomous agents with the intelligence that allows them to cooperate towards these common goals. So clearly, this is not something that you're unfamiliar with. There are many, many applications that would leverage or would benefit from this kind of technology. And we see these applications actually in the recent decade or so really shifting from research into industry. And that's really exciting for us, or for all of those of you who are working within the domain of multi-robot or multi-agent systems. So Amazon and here in the UK, Ocado are two of the flagship applications that are really leveraging a lot of the technology that is being developed behind multi-agent, multi-robot systems. We're also seeing more in terms of coordinated transport. So I think truck driving there is one of the trailblazers because it's been shown what the benefits can be in terms of reducing the number of drivers. Here in the UK, for example, we now have a shortage of drivers, not only due to Brexit, but also other reasons. And beyond that, just simply thinking about removing accident hazards and increasing energy efficiency by reducing the drag, given that trucks have such a large surface. Of course, agriculture has become more of a topic since we are putting the world or the planet under more and more pressure, and thinking how to optimize these systems and minimize waste is something where automation that actually has a physical component to it really can contribute to. And then, of course, there are many other applications that are maybe not fully fleshed out in the commercial domain and still have a strong foothold within academia, but arguably are exciting, and I predict that they will soon become interesting, commercial, and also commercializable and applicable within the next decade or two. So thinking of construction, space applications, and maybe in the near future, surveillance and environmental monitoring. And so what I do is really think about how to get all these various multi-robot systems to work together towards common objectives. And so I'd like to start off with a little bit of a movie that demonstrates a scenario that I find is good for motivational purposes. So this is a setup that we did 2-3 years back in my lab, actually when I just started as a faculty here at Cambridge. And we built these mini cars and we retrofitted them with our own computers and communication modules. Because what we wanted to do is actually design an experiment that would distill what the benefits are of cooperation in these multi-vehicle systems. And so we did a 2-part experiment. The first bit was showing how vehicles behave when they're actually driven by egocentric, like human-inspired controllers. And so what you see here is the cars essentially being driven by classical controller paradigms that are inspired by human-driven paradigms. And what you can see here is that as we block one of the cars in the inner lane, there is quickly a bottleneck that forms behind that car. And that bottleneck does not dissolve because the cars that are blocked in the inner lane do not find a safe space to merge out into the outer lane. Okay. And bearing in mind, the cars at this point, they're not exploiting any of the communication or intelligence capabilities that they were given yet. Okay. And so what we then did was we went about and designed by hand, essentially, a cooperative controller, which allowed the cars to talk to each other, to share incentives, and to coordinate with respect to their near future trajectories, what they were going to do. Bearing in mind that they have now one common optimization objective, which is to minimize traffic throughput. And so what you see now as the movie plays again is as the cars start queuing up behind the bottleneck on the inner lane, the cars on the outer lane actually execute a very subtle maneuver, which is to slow down and to make space so that the cars on the inner lane can safely merge onto the outer lane. And they do this because they're communicating and coordinating their trajectory plans with the cars in their vicinity. Okay. So this is a really nice example of what cooperative driving can contribute to. And what's nice is that it's not a simulation, it's actually an actual physical system. So it's a nice demonstration of, yes, this actually matters, and we can make these ideas work in actual systems that are not far from what we actually are starting to deploy in the real world. Now, although this is kind of neat and a great communicative element of what our research should be doing, the methods that we actually developed behind here were painstakingly hand designed, a couple of heuristics, and definitely tuned by hand, okay? And so the problem with this is that we can do this for individual applications and actually even go further and tune those individual solutions to the actual underlying work domain. But this definitely doesn't transfer to other problems, and it doesn't really present us with a foundational new method of how to develop cooperative solutions, right? And so this really segues into what our work is about, which is really about thinking of how to get robots to work together in ways that we can actually transfer these core solutions across many different target domains. Okay? Now, this is actually a really hard problem for multiple reasons. The first one is that it's been proven before that many of these coordinated decision-making problems actually boil down to problems that do not have polynomial time solvers. The second issue is that as soon as we start decentralizing the computation, we have to find out what parts of the solution space we have to communicate between which robots at which point in time. And there are associated questions with regards to what the convergence are of these solutions as we decentralize them. And these are questions that are not well answered. And the third problem is that even if we're able to solve points 1 and 2 here, this is making strong assumptions on, say, the messages or the information that is being passed between the robots, and what actually happens when these messages actually don't reach their targets, their destinations, and what happens when there is noise in the system, or what happens when these systems are actually hacked and compromised from the outside. So there's a lot of associated problems that we think we have to tackle in conjunction to actually developing the solutions as we go along from application to application. And so we've been thinking a lot about taking a data-driven approach towards these problems because of many of the aforementioned challenges that we are encountering within this domain. Whereas what I mean by data-driven is not necessarily purely data-driven, but potentially also hybrid approaches where we inspire from first principles approaches, but still there's always some element of the system that happens to be a data-driven one. Our go-to architecture is going to be the graphical network, and I will talk a little bit more about that in the next few minutes. And our learning paradigms are either imitation learning or reinforcement learning. And what we are trying to do here is we're really trying to get the performance out of these systems that are very close to what we would get from centralized solvers, so our actual optimal solvers. But then we have solutions that scale much more gracefully, or that can solve instance sizes that wouldn't be possible anymore with our counterpart centralized solutions. So this is the contribution that we're bringing in. So to summarize this, the research agenda is really guided by the overarching question, can robots learn to coordinate? And this agenda is fueled by this very simple insight that robot relationships can be represented by graphs. And this would actually allow us to exploit the structure of graphs and represent these agent-to-agent relationships as such. And why this is helpful is because this graph structure allows us to organize the data, which, as we know from the machine learning community, as soon as we have ideas of how data can be organized, this significantly facilitates the learning problem. And so what is it that we're going to try to learn? Well, what we're trying to learn here is the communication strategy. So what are the individual agents going to be communicating? And how are these agents then going to ingest the incoming messages, so the latents that are then going to be communicated amongst each other to inform the decisions they make locally on board. So those are the two things that we want this learning architecture to answer for us. So as I mentioned before, the learning problem here is going to be based on this machine learning architecture known as graphical networks. And I presume that many of you will have heard of graphical networks previously because they have been used very broadly within the machine learning community within the last decade to model structured input. Classical examples or famous examples consist of researchers who have used them to model chemistry applications. So molecules are very nicely represented through graphs, or even, for example, by representing fluid dynamics through mesh-based approaches. So those are two application domains that lend themselves very nicely to this kind of representation. And in a similar vein, we're now going to use these graphical networks as a proxy for representing our underlying system, which in this case is actually the interaction network, or in other words, the communication topology, right? Since we're talking about agents or robots talking to each other. And what we're going to do is we're going to have these GNN perform operations in a topological space that is then defined by these agent neighborhoods, right? And so GNNs have several interesting features. One of them is their permutation equivariance, which basically means that the same action is taken if the state of neighboring nodes within the same topology is the same. They're also stable in the sense that if neighborhood topologies are similar, then similar actions will be taken. And we know that through the mathematical formulation of the system, we know that it is intrinsically distributable. And I will say a little bit more about that in a bit. So those three things together make GNNs a very interesting paradigm for us to use, or architecture for us to use towards this high-level goal of trying to teach our robots how to coordinate with each other. And so what I'm going to speak about today in my talk is essentially three main things. So the first thing I'm going to talk about is how we've been using GNNs to solve a couple of hard, so in the classical sense, coordination problems. The second thing I'm going to talk about is how when we then shift to a reinforcement learning paradigm, if we're not careful about how we design the training scheme, we can actually also elicit bad communication or bad coordination policies. And that example really serves us as a stepping stone to understanding what we have to do when we design these systems to make sure that the end goal is actually what we were hoping to achieve in the development of these systems. And the final thing I'm going to talk about, which is arguably really important, is a lot of these things happen in simulation first, especially because we're at the very beginning of this journey of using graph nets or machine learning in general towards multi-robot learning, is what do we do about the distribution shift? So obviously we're getting these fancy policies, but they've been designed in simulation, tested in simulation. But what we want at the end game is for it to work on real robots. And I'm going to be showing you some very new work that has just come out of my lab, showing you how we are thinking about this third challenge. Okay, so let me talk a little bit about how we're solving some hard coordination problems. So the first research challenge we decided to tackle when we started working with GNNs is the problem of multi-agent pathfinding, where we asked the question, is it possible to automatically synthesize local communication and decision-making policies to solve this very hard coordination problem? And so why this is really interesting, the multi-agent pathfinding problem, is because on the one hand side, we know it's NP hard for either make span or flow time. And on the other hand side, well, we actually have the optimal solvers for small scale instances. So we can actually benchmark our solutions really nicely at the beginning of this journey where we're trying to test what architectures and whether this approach even works, right? So it lends itself as a very nice first problem to try to tackle with this new idea or approach. So how do we set up the problem? Okay, so the things that we want to do here is we want to derive a local policy, right? So we want the agents themselves to be making the decisions based only on what they know locally. And the decision-making processes here are going to be local as well. And so we impose this local visibility area, which is shown in light green here, where the agent can see obstacles in its vicinity, and it can also see any other agents that might be in that local field of view. And we also say that, well, actually our agents don't have global positioning. All the agents will know is a direction to their goal position. And this is simply translated as a point on the perimeter or the periphery of this local field of view. And so they're always able to head in the right direction, but they don't explicitly need to know where they're located nor where the goal position is located. And the final thing that the agents have to their disposition is the ability to communicate with other agents that are close by. And so what we're trying to do is we're trying to now going to teach these robots to operate based on what they're getting and reach a performance that is hopefully very comparable to the kind of performance that we would get with centralized solvers, right? Yet the holy grail here is that if we're able to teach and train these policies on small systems, we can hopefully take these very same policies and scale them to systems that would then compute much more efficiently than we could do with centralized solvers. So what does the architecture look like? So we have three main components in our system where for each robot in the system, we input a tensor that is recording local information, here composed of the observation of obstacles, of your agents, and the goal projection. That information is then locally encoded by a CNN, and the GNN then emulates the communication by computing how the information is then sent and received among agents. And that output is then fed into a sequence of fully connected layers. And here, because we're considering a discrete action domain, we're looking at outputting a robot's motion decision as a function of up, down, left, or right, or idle decisions. And we do this as a result of a softmax activation layer over the discrete motion primitives that the robots have. And so what I'm going to do now is I'm actually going to write down the model for the GNN in a centralized form so that we have a grasp of what the system actually looks like, to then in the following slides convince you that the centralized formulation actually executes in a decentralized manner. Okay? So in the first equation, what I'm showing you here is the basics of the system, where S is my adjacency matrix, so which agents are talking to which other agents, and X is my matrix that is gathering the observations from all the other agents. And the equation is actually telling me how an agent I is aggregating information that is being sent to it over a number K communication hops. Okay? The second equation then parameterizes this message aggregation by right multiplying it by right multiplying the observations with the matrix H, which is actually our learnable parameter here, right? And G is essentially our communication function, and theta2 are its parameters, right? And so this part here represents the communication part of our learning scheme. But recall that I mentioned that we're actually pre-processing and post-processing the latent that goes through the comms network. And these two networks as well have their own parameters. So the CNN is parameterized by theta1 and the MLP is parameterized by theta3. And so overall, I have these three functions. So I have my encoder, my decoder, my encoder F, my comms function G, and my action function essentially H. Each of them are parameterized. And I'm going to be computing a loss function that takes in my optimal actions. And since I'm functioning in the discrete domain, this is actually a cross entropy loss here. So this sets up my system. And now I'm going to try to show you how the system here functions when I'm actually running it locally on board individual agents. Okay? So here I have a simple system where I'm representing three robots, A, B, and C, and I'm showing how they're making their own observations. So for agent B here, this would be this observation encoded by Z subscript B. That observation is separated into three channels here. This is actually a detail, but it was convenient for us, where each channel represents one slice of the information. So one channel represents the agents, another one the objects, another one the goal projection. The CNN codes this information and gives us this latent vector X sub B. And that latent is what the agents are going to be sending to each other. So agent B does it, agent A does it, and agent C does it, and they're all sending this information to their local communication neighborhood. Now, at the next step, and this is the interesting part, is how is that information going to be processed? So we're looking at this from the perspective of agent A. Okay, so let's assume that our ego agent is now agent A. And what agent A is going to be doing is it's going to be receiving, well, it has its own latent that it computed itself based on its own observation, but it's also receiving latents from B and C because they were in agent A's communication neighborhood. And so for all information that is coming in from these various hops, what's happening is that this information is being summed and being multiplied by a matrix, which is H, which is the learnable parameter that I described before. And then it's being summed up and passed through a nonlinearity to produce X prime sub A. And that then gets fed through the MLP, which is the same for all agents, for example, because they're doing parameter sharing here. And you see now how this architecture is running completely in a decentralized way on agent A, based only on the latents that are being sent to it from its local communication neighborhood. Okay. So I hope that this gave you an idea of how we're taking the centralized formulation, but actually running it in a decentralized manner on board individual agents. And so what I'm going to do next is I'm actually going to show you a movie that shows you and juxtaposes our solution, which is now on the right-hand side, with the solution computed by an expert solver. So on the left-hand side, we actually have an algorithm that is taking in full centralized, full observability of the full problem and computing an optimal solution. On the right-hand side, every agent is actually computing its action in a sequential decision-making kind of manner based on decisions it makes at every time step, given the local observations that it's making. And of course, on the incoming information. And so just for the sake of visibility here, these lines here represent the communication topology for one focus agent. So right now you see it for agent 20 and its two-hop communication neighborhood. And there's a lot going on in this movie, but what you can qualitatively observe is that the expert solution and our solution, they both finish at roughly the same time, which is a good thing, because qualitatively it means that our agents are running at roughly the same speed with paths that are similarly efficient. And you can see that the trajectories that they choose also qualitatively look relatively similar. So this is a good thing. Of course, we then went on to analyze this quantitatively. And so what we're doing here is we're benchmarking our solution with respect to the expert, which in this case, we chose CBS, which is short for conflict-based search, which is one of a few solvers that exist towards solving the multi-agent pathfinding problem optimally. And we're also benchmarking it with a fully distributed version, which is ORCA, so reciprocal collision avoidance, which we adapted slightly towards our problem, which is in the discrete domain, whereas ORCA, the original version, is for the continuous domain. And what you can see on the left-hand side is the success rate for our models. And you can see that for our best model, we're around 100% throughout different robot size instances. And by success rate, I mean here, it's actually a very rigorous metric, because if I have, say, 12 robots and only one of the robots doesn't reach its goal, that actually counts as a failure, even though all the other 11 robots reached its goal. So it only counts as a success if the full system fully satisfies the problem specification. And on the right-hand side, what we're seeing is actually flow time increase. Right. And so for computing the flow time increase, clearly we have to compute the solution given to us by CBS as well, so that we can compute these comparative metrics. And so for our best system, which is given to us by a GNN with a higher communication hop count, we're staying at a flow time increase that is extremely low, so which is a good thing. And it stays relatively flat as we increase the size of our robot system. And so you're probably wondering, okay, why does our scale finish at 12? Well, the reason that it finishes at 12 robots is because we're computing comparative metrics, which rely on the existence of an expert solution for these respective systems. Now, clearly, we want to go and solve these systems for much larger problems than just 12 robots. And at that point, we now have to relax the way we compare performance, because we can no longer rely on CBS to provide these solutions, because CBS is intractable given a 10-minute timeout for instance sizes of more than 40 agents, say. We actually followed up on that particular approach that I presented to you before, for systems where we actually stated a more ambitious goal, where we wanted not only to scale, say, 2x in size with respect to training instances, but actually more like 100x in size. And what we realized was a problem for us is, as you scale these systems up and as you increase the communication hop count, there's actually a lot of information coming in, and it's not clear how that information is being ingested by the agents to help them make the best possible decisions to reach their goals as quickly as possible. And so what we added to our architecture to facilitate the agents to still remain focused towards reaching their goals and avoiding deadlocks with other agents is we decided to add a attention layer to our system, which is here represented by an additional learnable parameter that allows the agents to deal with this potentially large amount of incoming data, right? And what we can see, and what it's essentially doing, is it's essentially learning a pattern of when to pay attention to which communication partner as a function of individual agents' local features and features that are represented by their counterpart agents in the vicinity. And so what we can see here in the results is that the attention-based GNN is able to scale to much larger systems than our counterpart GNN, so our best solution from the prior approach, as we start scaling to much, much larger systems. So if you look at the right-hand side plot here, as we're scaling to systems that are at least 100x in size, the classical vanilla GNN starts to drop significantly in terms of the percentage of the number of successful agents at their goals. Whereas the attention-based scheme stays close to 100% in terms of that success rate. And so this is promising because we have a system that has learned to synthesize these local policies, but we also have a system that allows us to scale these kinds of policies and pay attention to important information as communication networks become denser and larger amounts of information is incoming. So now I want to shift slightly in terms of the narrative of this talk and talk a little bit about other aspects of what happens when we're trying to teach agents to communicate with each other. And what I'm going to show you in this next study is that actually we can show that it's not so difficult to elicit an adversarial communication that can actually impede cooperation in multi-robot or multi-agent systems. And so the research question here was trying to understand how these adversarial communication policies emerge when we're devising these schemes through the reinforcement learning paradigm. And the case study that we decided to use here, because it lends itself very nicely to describing this or to studying or analyzing this problem, is the problem of cooperative coverage. In this case, a non-convex environment. So what is it that we want the agents to do? So ideally, what we want to happen here is we want our agents to communicate and to coordinate so that they distribute over this space in order to cover this area as quickly as possible as a team. So you'd assume that as a function of their initial positions and as a function of how many agents there would be some manner or form of uniform distribution across the area and coordination so that agents distribute to cover previously uncovered areas. So that's the expected performance. And that's kind of the pattern that you see happening here in this movie here, because the agents are successfully coordinating to do such. And you see the coloring of the area does represent exactly that idea. So the coloring seems to be relatively well distributed across the agents. Okay, so what we wanted to do is we were interested in seeing the agents jointly decide where or which agent goes where to cover this area as quickly as possible in two different area types. So one is this non-convex area with obstacles arbitrarily distributed in this area. And the second area type that we were interested in was the split environment area type, where agents are only rewarded for covering zones in the right-hand side of this environment. The reward or the agents, the reward that the agent basically ingests in both of these systems is simply by covering a previously uncovered cell. Okay. Now, the observation, crucially, that the agents make is local. So they know the areas that they themselves have previously covered, and they're able to observe what other agents are around them for simple collision avoidance, but they don't know, unless they use explicit communication, they don't know what areas other agents have covered. And that is where the communication policy comes in. So they need to communicate with each other in order to coordinate where they're going next in order to reduce the redundancy of covered areas and coordinate as effectively as possible. And so what we're going to do is, because we're interested in studying the emergence of potentially adversarial communication strategies, is we're going to separate our team into two teams. We're going to have a blue team and a red team. And these two teams are going to be trained in a slightly different manner. Okay. Although although we're going to have both teams programmed with this exact same reward function. So it's simply the agents are going to be rewarded by covering uncovered cells, and that is the same for both teams. So let me just formalize the system before going to the details of how we're going to set this two-team system up. So very similarly to before, I again have three key functions that I'm going to be learning. So we have function F that encodes these observations that my agents are making. We have a function G that represents the communication strategy. And we have a function H that is going to output the final action. Different to before, however, we're going to formalize the GraphNet so that each agent team can actually learn its own set of parameters. So here you can see that I have a superscript on my matrix H, which is giving me the opportunity, the possibility to learn an H per index I, in this case, agents. Okay. And so what we're going to do is we're going to have agents hold policies pi, which we're going to improve through a policy gradient with the goal of maximizing cumulative rewards. And the key here is that we're really going to make it explicit in this formulation that the actions taken by other agents will affect the reward of each individual agent. Okay? And we're going to make it very explicit that there are essentially two teams operating with two sets of parameters. Okay? So we have theta superscript m for one team and theta superscript c for the other team. And what we're going to do is we're going to first train a system where we're only interested in learning one set of parameters, so theta superscript n for the red team, whilst holding theta superscript c fixed. So we're going to train theta superscript c, then hold it fixed, and then we're going to train theta superscript n a posteriori, okay, after the theta c is fixed. And we're going to analyze how the communication strategy evolves as we perform the training in this manner. Okay? And so I'm going to start by showing you a movie of what happens. So on the left-hand side, what you see here is the result of when we actually train the red and the blue team simultaneously. So theta n and theta c are being learned at the same time. So essentially indistinguishable. And on the right-hand side, I'm showing you what happens when we learn theta c first, fix it, and then we actually freeze those weights, but we leave the theta n weights continue to adapt as a function of time. And so what's really interesting here is that without specifying a reward that is actually adversarial, because the reward is totally benign in the sense that the agents simply get rewarded for covering uncovered cells. With that very simple reward, the red team learns how to exploit the fact that it's able to propagate gradients through the communication channel, to learn how to manipulate the other agents to covering areas where it's able to keep them out of its way, right? So the red agent is essentially learning to communicate to the blue agents where they should head so that it has more area for itself and hence reaps a higher ultimate reward. And training this policy in this environment also generalizes to executing this very same policy in a larger environment with the exact same communication strategy. So you can see on the right-hand side again here, with only one red agent on the red team, its communication policy is effective enough that it can keep the whole blue team constrained to the lower left side of the environment that they're supposed to be covering, hence reaping the reward of the upper right-hand side of this area and performing higher than the blue team is. Okay. So this is very interesting to us, and we of course looked at this quantitatively and saw that the training pattern coincided with what we were observing as we rolled the policies out at runtime, where you can see that as on the top-hand side, 1/3 through training, as we fixed the policy of the blue team and allowed the red team to continue learning, the red team was really able to learn this manipulative communication strategy that allowed it to reap this higher return than the members of the blue team. And what you can see on the bottom plot, which is showing us the return as an episode progresses, averaged over 100 runs. So this is averaging over execution of the policy. The solid line is actually showing us the values for the policies we obtained at the end of training. And as a comparison, the dotted lines show us the values when we actually are cutting the communication channel between the red agent and the blue team, right? And what you can see is that as this communication capability is disrupted between red and blue, the red agent's performance drops back down in the order of what the blue agents were able to do. So really confirming the fact that the red agent is exploiting the communication channel to send over manipulative information to the blue team in order to keep them in check. And so, as I mentioned before, without communication, the red agent is really not able to exploit this manipulative strategy that it has learned it can do when it does have communication available to it. And we went a step further because we were interested in, okay, how does this come to be? We had an intuition of what it might be, but we wanted to see this visualized. And so what we did is we trained a post hoc reconstruction of the messages that were being sent between agents. So what we're doing here is we're trying to visualize the latents that are essentially representing the messages that are being sent between the agents. And what we saw was interesting in the sense that if you look at the top right-hand side, the top row here, what you see is that's the ground truth coverage that the agents did during their coverage performance. And what you see on the bottom side is what they actually sent to the other agents, represented through our post hoc interpretation method. So the latent represented here. And for the blue agents, you see that they coincide. So the ground truth coverage coincides with what the blue agents are communicating to each other, right? So if I cover this area, I'm going to tell my colleagues that that's the area I covered so that they can effectively coordinate and base their decisions on that true fact. Whereas for the red agents, we can clearly see that the interpreted messages are lies. So they don't correspond at all to the ground truth local coverage that the red agents have executed. And so this is interesting and also kind of neat, because we see that it is indeed through a sort of a lying strategy that the red agents learned to exploit the communication channel to manipulate the policy or the strategy that the blue agents are executing at runtime. Okay, so this kind of summarizes the bit on why it's important that we think carefully about how we're actually training our agents when we're allowing them to learn the communication. Especially if we cannot necessarily introspect the messages that are being sent, because we need to keep control over what the end effect is going to be of the messages that are being ingested. We actually developed something, and this is ongoing work, along the lines of, well, even if we have adversarial systems or systems where agents are potentially sending each other non-truthful or manipulative information, isn't there some sort of protective mechanism that we can design in order to counteract that? And we had this very simple idea that actually there is a way of providing robustness against faulty information. And perhaps the idea of providing this robustness is not so far from simply the idea of filtering. And so what we decided to do in this system is say, well, say I have a system where I actually also have some side information. For example, I'm receiving information, I'm ingesting information that I can't necessarily interpret from from the agents around me. But what I can do in a safe and secure way is I can potentially observe something else about those agents. And so what we said here is, well, what about if I can observe their relative positions with respect to where I am? And it turns out that relative positioning is actually very powerful because it can tell me something about the context within which the messages that are being sent can be understood. And so what we did is something actually very simple. What we did is basically to say that, well, we can actually use the side information, so here being the relative positioning, to build a model that characterizes the mutual information between agents given this relative position. And this model will be able to tell me whether or not incoming information is plausible or not, right? Because if you look at this little image that I'm showing you there, if I see an agent to the right of me, and that agent is telling me it's seeing the wing of an airplane, right? If that's what the agents are trying to piece together here, but I know that it's impossible that that agent is lying at a position where it would be able to see the wing, then I can probably filter out that message and discard it as likely being false, right? So that's kind of the underlying idea here. And mathematically, what we do is we use this model to compute the posterior probabilities and interpret this as a confidence weight, essentially, that tell us whether or not a communication partner is being truthful. And we integrated into our GNN very similarly to what I did in the prior work when I described to you this attention mechanism that we're using in order to focus on relevant information. So here the attention is computed as a function of credibility of information. And that allows the agents to downweight income information that they think is likely to be non-truthful or not helpful to their decision-making, and essentially suppresses the influence of any information that is being tagged as suspicious looking. given some side information of or some side channel of other information that the robots or the agents would have here. And we can use this idea and re-perform the coverage example that I showed you before under the influence of an adversarially trained agent. And you can see that on the lower plot here, when we use the filtering scheme turned on, the red agent's performance is mitigated. So we're now at the level of the performance that the blue agents can achieve when they're just communicating and interacting with each other. And of course, if we turn the filtering off and the red agents' messages are not being filtered, they're able to outperform and control the blue agents to their advantage. Okay, so this kind of ends the bit about that I want to talk about in terms of learning adversarial communication policy. And I want to shift over to the last bit of my talk, which is arguably almost the most important part, which deals with the problem of, now that we know how to develop or to train policies in simulation, how do we deal with the distribution shift as we move to real-world robot systems? And so what do I mean by distribution shift here? Well, clearly we're training these policies under idealistic settings where we're running our simulators and all the training environments in lockstep without communication delay, without noise, without all of these characteristics that tend to happen in the real world. And hence we do not have any guarantees, or we haven't observed or quantified what would happen when we actually roll out these policies in the real world, where suddenly the distribution of what the graphs look like is quite different. And also the intermittency of the edges in that graph also behave quite differently. And so what we wanted to do is to test the sim to real on a policy that we train purely on simulation, on an example, which is what I like to call a make or break example, right? And it's make or break because what I want my agents to do here is I want them to coordinate to reconfigure their formation so that they can fit through a constriction. So in this case, a very narrow passageway where only one robot fits through at any given time. And the robots here, they have to get through there as quickly as possible. And so in order to do that, they have to somehow negotiate how they're going to form the line so they get through this passageway, right? And so it's a make or break because either they collide into each other or they don't get over to the other side of the passageway, right? And successful coordination here means they need to coordinate in order to get to the other side. And so if the sim to real challenge fails, then the robots are not going to be able to solve this task. And so we were interested in using this toy setup or this very specific case study to understand what are the real world conditions that would lead to policy transfer issues, and whether we're able to actually identify and isolate the causes for the domain shifts. And finally, do those two insights help us to actually develop methods that allow us to more gracefully transfer policies trained in simulation to the real world, hopefully through zero-shot transfers or minimal tuning. And so what we did is something I thought was quite interesting and systematic, in the sense that we decided we would go through this shift through 4 different individual steps, right? So the first, by considering 4 different modes of communication. And there is some nuance to this. So there are 2 classes. Clearly, one is the centralized class and one is the decentralized class, right? So in the centralized class, we basically have a computer that is computing in a joint state space the action policies for all the robots, sending those action policies to the router, and the router then just broadcasts that to all the agents or the robots in my system. So that's my centralized scheme. And essentially, if I'm running it in a decentralized scheme, everything is still able to run in lockstep on the computer because we're essentially simulating everything under idealistic conditions. Now we can decentralize the system by just making it one notch harder by saying, okay, I'm going to run it in threads on my centralized computer. So now I no longer have synchrony that is guaranteed because I'm threading my system. But then the actions that the robots have to execute are then being sent to a router, and the router manages the communication to the robots. So it's decentralized, but still kind of nicely managed by one kind of communication infrastructure that is dealing with the propagation of the messages. I can take it another step and say, okay, now we're going to go fully decentralized in the sense that I'm going to be running the policies on board the robots. So the compute is now on the Raspberry Pis that the robots are carrying. But the communication itself will be managed through my local networking device, which is here, my router. So messages are sent to my router, and my router then broadcasts them to the agents. And the final scheme, the final mode that we were interested in is we're going fully ad hoc. So that means I no longer operate with a router. I have comms modules that operate in a point-to-point manner individually on the robots, and they're really only communicating with other robots that are within communication range. And that communication range we can actually control, because we can control how far these individual comms modules are able to reach to. Okay. So those are the 4 modes that we're going to consider in an experimental setup, and we're going to analyze whether or not our policies degrade as we relax the centralization assumption in these systems. And so I'm just going to play this movie that shows you how we step through these modes, and visually showing you whether or not the policies degrade. And so what you can immediately see here is, so here we're actually showing you the final results, right? So the robots moving through the passageway. This is just describing the system. And what we're showing in the visualization is an overlay of what the simulation is predicting the robots should do, right? So that's coming from what we compute on a PC, to what the robots ideally should be doing, to what the robots are actually doing in the real world. So you have those 3 pieces of information that we're overlaying in the actual footage of what's happening. And we're looking at the 2 extremes here. We're looking at centralized mode and the decentralized mode in fully ad hoc. Okay, so in centralized mode, you have the router taking the commands that are computed by a PC, telling the robots what they should do. And clearly here, this is a successful scenario where the robots reach their goals. They're a little bit slower than what the simulated policy would have done. But as you can see qualitatively, it's very close to the kind of performance we would be hoping the robots to get. Now we decentralize the system and we go to fully ad hoc. So everything is being performed on the robots and they're relying only on ad hoc communication. And what's really nice here is that you can see that the performance is extremely similar, at least qualitatively. The robots reach their goals in a similar manner as they did for the centralized version, and the cases are by and large successful. So they fit through the constriction, they successfully coordinate, and they all eventually reach their goals. So this is really cool. And we went, of course, and analyzed the data quantitatively. And I realize I'm soon out of time. I'm going to wrap up in just a few minutes. And we were interested in seeing how this performance compared as we relaxed the centralization assumption from fully centralized through the 4 different modes to the fully ad hoc decentralized scheme. And on the top row, you can actually see how the make span shifts as we increase decentralization. So the shift is very subtle, but you do see a slight shift from the simulated version, which has a very strong peak on the left, so very short and quick make spans, to the onboard ad hoc system, where we have a slightly heavy right, so a shift towards the right-hand side of my time axis, showing that the robots do tend to take a little bit longer to complete their mission. What our quantitative results also show us is actually really interesting in the sense that, so yes, there is always a drop in performance as we go from simulation across the 4 different modes, and the drop increases. So the drop in performance increases as we go from centralized to offboard to onboard over infra to onboard over ad hoc. But what's actually interesting here, there are 2 things. The first thing is that success is higher when we're in ad hoc mode than when we're doing onboard over infrastructure, which has to do with when we're actually doing point-to-point communication. The robots have a more effective way of getting over message contention issues, which are more of an issue if we're piping everything through the router. So that has an impact. And the second thing that is interesting in these results is that if we enable the robots to communicate in a fully connected network, which is the second to last column here, and you can see this, the success rate there being 66.7, it's actually worse than when they're in constrained communication networks in the prior at least compared to the ad hoc version. It's similar to the onboarded infra. And the reason for that being simply that during training, because the robots are running on simulated policies here, or policies learned during simulation, the robots never experienced fully connected networks. And so the distribution shift here has an impact. So it's not simply a question of giving the robots unlimited capabilities, it's more a question of giving them capabilities that correspond to the capabilities that they saw or experienced during their training in simulation. So overall, very exciting, because we showed through our make or break scenario that our policies transfer in a zero-shot manner from simulation to real without any fine-tuning at all, albeit with a slight performance degradation. But overall, we think this is really promising, and that we can also isolate the individual issues and improve with respect to individual issues to get as close as possible as the types of performance we'd hope to gain from these systems, given performance that we see in simulation. And so this brings me to the end. So I just have a few take-home messages for you. So the first is clearly that we think that graph neural networks really facilitate the learning of distributed policies. We find these machine learning architectures extremely powerful, especially because they're able to provide us with intrinsically decentralized policies that end up with extremely powerful local decision-making strategies. Powerful also in the sense because we've shown that they generalize to problem size instances that we cannot tractably solve with many first principle solvers. And we've also shown that we're very close to understanding what it takes to make these policies transfer seamlessly from simulation to the real world. A few things that I'm excited about. So clearly there are many. But three of them are explainability, fairness, and resilience. And I'd like to point you to some interesting work from other PhD students of mine that delve into these topics in more depth. And perhaps it maybe in the broadest sense, point you to a survey paper that we wrote on resilience, where we tried to distinguish and delineate robustness approaches from approaches that actually provide resilience. And we point to the fact that actually networked or multi-robot systems are in an ideal spot to actually provide resilience, where simply considering single agent systems would not be able to provide the same kind of capabilities or solutions to problems that require resilience, which is a step higher than robustness. Okay, without further ado, I'd like to thank my team again, and would like to thank you for your attention, and would be more than happy to take any questions at this point. Thank you.
Thank you, Amanda, for the great talk. Let's open the stage for questions. Do you have any question? If yes, you can simply unmute yourself and ask.
Hi, I have a couple of questions.
Yeah.
So the first one, near the beginning, where you talk about the concept of graph neural networks. I think what's not clear to me is how you go from fixed topology, like a mesh topology, and then it's easy for me to understand what it means to be equivariant in that mesh, versus when you have what seems mysterious to me is now you have robots moving around with an arbitrary topology, and the topology is changing. That is, if you could explain that. Thank you.
So I think from a mathematical perspective, the key thing is what the graph neural network learns is essentially, if you recall the slide where I showed you how the information is being ingested at the local scale, the parameter that I've learned, H, is actually being applied to a sum of incoming latents. And what that means to us, if you think about this in graph terms, is it doesn't matter if I have 1 or 2 or 100 edges incoming, because the latents are being summed up before they're being multiplied with the learned tensor, right? So that is mathematically maybe the part that helps you make sense of, okay, the tensors are decentralizable, right? In the sense that It doesn't matter how many incoming edges you have. And then the follow-up question you then have to ask is, okay, so how do I deal with this? Because obviously these tensors are being tuned during training where potentially the graphs look one way, and then when I execute, they're looking another way, or I have time-varying topologies. Well, the key here is that the patterns that the GNNs observe during training have to be roughly similar to the patterns that you'd observe at runtime. And that's where the sim to real challenge came in, and that's what the last part of my talk was about.
Mm-hmm.
Does that make sense?
So if I understand, almost.
Yeah.
So could you just show me the slide, please?
Sure. Sure.
The slide you're referring.
Yeah. I'll go up to that.
So, okay, maybe my refining question is: it's hard to understand what is the expressivity of these operations that understand mostly linear operations. So, for example, like are the contributions from all the agents summing linearly, or can you express something like if the farthest agent tells me this, then I do this? Like, what is the expressivity?
So there are, yes, I see. So there are different ways that you can perform the aggregation of incoming messages. And I think that's a broader question that I didn't address in the talk today, and perhaps also is more suited to an offline discussion because there's work ongoing in that domain. But this paradigm that we used in the papers that I've showed you here is a simple sum aggregation over latents coming in per communication hop. And the tensors are learned per communication hop. So you can see here, I have my H subscripted with indices. Here, each index corresponds to one communication hop. So I'm learning a pattern per communication hop. And then it doesn't matter how many incoming messages I have per communication hop, because those are being summed before I multiply it with that tensor, with that matrix H. And the nonlinearity happens after the sum over all communication hops. Yeah.
So, maybe my question also includes the following. So you just look at do you know where the other agents are, or do you just know how many hops there are away?
So your question is, do I know where the agents are? That question actually goes beyond the pure GNN question to what is, how do we set up the learning system? So in our case, we have an end-to-end learning scheme in the sense that, so if I go back here, right? So our loss function computes a loss over the action, which is the ultimate action that the agents take. And we're training 3 sets of parameters simultaneously, right? So we're training the encoder, we're training the comms, and we're training the MLP. The MLP is the one that outputs the final action, right? So the reason I'm saying this is because you asked me a question about, do the agents know where they are? Well, it depends what I'm inputting the system. In this case, my local observation was, no, there was no absolute information. There was only a purely local observation that was not anchored to any absolute system at all. So I had this 3-channel input, which corresponded simply of local field of view, agent positions, goal direction, and that was compressed by a CNN. Now the CNN is obviously trying to compress this information in a way that then becomes useful to the other agents, because the latent that comes out of my CNN is what is then being communicated to other agents, right? That's what goes over the communication topology. And on the incoming side, right, when I receive a latent from any other robot, that's when I'm multiplying that incoming latent with H. And H is my comms strategy, essentially. I'm learning to interpret what another agent is telling me, right? So everything is chained together here. So the agents are learning to encode their local observations in a way that it's useful to other agents when they receive it on the other side of the comms channel, right?
Okay, I have a connected question, which is, you showed us that you make a design choice, I think, in how you represent communication.
Yeah.
With these three layers, and so question
at the
one
very
is,
end, at the very end of my talk, or
no, in the middle. I think you showed that, like this. So one is the object, one is the position,
the channel, yeah. This
the channels, yeah.
Yeah.
So okay, basically, I mean, why? So is this something that makes it easy?
So it's a good question. So I am not an expert on CNNs, but we decided to choose a CNN for the encoder network. And one type of incoming representation that CNNs can deal with very elegantly is when you have multi-channel information. So CNNs were originally developed for processing image information, right? And you could, for example, imagine having a channel for color information, a channel for something else, and you separate that information into these three different layers. And we just decided to use the same kind of architecture because it was well suited to the CNN choice that we did. I don't think this is a make or break design decision. You could perhaps replace this with an MLP and have a flat input, but we didn't test this. We didn't do. Okay.
So actually, I understood that this was you were putting some structure on the communication format somehow.
No.
So okay, my general question is, all right. So I think I'm convinced that we can take a very complex problem like this one.
Yeah.
Find the right way to encode it, which I think is the difficult part. Basically, and then using known building blocks from machine learning, and then obtain something that works. My question is, okay, how should we think about interpretability in the sense that, for example, imagine now there's a mixed human robot team, right? So maybe you want to have some. I don't know. Is this like interpretability? You can add as an additional constraint, or would you, for example, choose the messages they can send? How do you think about this?
No, I mean, I think your question is spot on. I think it's really important, and I think this is so. We actually have ongoing work on that. Partial work that I showed you today actually goes into that. So if I go forwards to this little add-on that we did on this study, right, that is moving towards that direction. So we did post hoc interpretation. So we have our latents. We trained a network that was specifically trained to interpret the latents as coverage, and would then be able to reconstruct any incoming informations as with an output that corresponds to a coverage map, right? So this is one way you could think about interpretability. But obviously you want to have a more foundational strategy that provides you application and variant ways of providing interpretability, or maybe what you're addressing is maybe even forms of guarantees with respect to what like if I'm communicating something, does that correspond to what I'm actually going to do? So I think this is ongoing work, not only from my team, but from other teams looking into this. And I think it's exciting. So I think with this, what I'm showing you here, you can already imagine that you could have a robot human team working, right? You could have an agent sending out, this is what I've covered locally. A human could inspect this information and base its decision based on that, or base its actions based on that piece of information. So I don't think I think it's for visual, for problems where we can visually represent the information that is being sent through, that is contained in our latents. I think we have an easier task than for problems where the information we're sending in our messages is not visually representable. So for more complicated information.
Yeah, very interesting questions.
Right. Is there any other question?
There's one from the chat, I think.
Yeah, exactly. So in the chat, there is Wei Wang. I don't know if she or he is still here. I don't think so, but we can ask it anyways, I guess.
She's online.
Okay, sorry. Yeah, sorry. I'll repeat the question maybe. For the part one of the talk, will the one-step hop become a two-step hop and vice versa during the moving? And the question was because the distance between the agents keeps changing.
Yeah. Yep.
If so,
Absolutely.
how?
Yep.
If so,
yes, yeah, that's a great question. So we at design time we say that agents have a communication range, and the hops are defined as a function of this communication range. So if agents are within a certain distance, so we're assuming a disk model, right? Essentially, and when agents are within this communication range, then we facilitate the communication network that corresponds to those inter-agent distances, essentially. And that's that the distance is fully defined whether or not an agent is within one or two communication hops.
Let's see. Wei, could you please?
Oh yes, sorry, I was listening. Yes, but so there's not the distance related. It's more like how you define the one step or two step, because I saw when you showed the movie just now, like in the image, it's more I feel the one step hop never didn't really change. It's more changed. It's two step hops. Or maybe I saw it wrong.
Yeah, no.
Yes.
So the communication topology changes at every instant the agents move because it's fully distance based, right? So there's no doubt about that. But what you're referring to is the actual hop, or I don't know if I understood the question correctly, but what number of hops we consider, that's a design decision. So we can say we're deploying a robot system that is only enabled to communicate within one hop, and then we're running a communication policy that only has H subscript 1, right? And not all the remaining other parameters that could have been trained for the other remaining hops. So you can say that your communication network is only one hop enabled, for example.
Yeah, but like what I saw there, it's like even though some agents, it's getting closer, but they are still at the two-step hops like communication. It's not.
Yeah, so you can see here how the red. So you can see how the agents reconnect to new agents all the time, right? So
yes.
And as they move away from each other, the red edges, they cease. So that's showing you how the communication topology reacts.
Yeah. All right. Yeah. Thank you.
Yeah. No, thanks.
All right. Any final question?
I would have one. So first, thanks a lot. Really cool talk.
Hey, Florian. Good to see you.
Hey. Yeah, good to see you too. So obviously the thing I'm most interested in is the adversarial part where you have malicious agents, because that was a bit close to what I did in the past, or at least I felt like that. The thing I was interested in is how the agents in this example deal with contradicting information. So you only have one agent communicating like this malicious information, right? And it's still able to overrule all the others. So how did that come? And
that's a really good question. We did not analyze that. That's to be completely honest with you, but it's it boils down to exactly what you're asking. So in our case, when the agents receive information from both the adversarial as well as all the cooperative ones, there is no way for them, they're not prioritizing over any other messages. It's simply that all the blue agents are receiving messages from the adversarial one, and that leads to them functioning well. They're all being sent. So here you can imagine they're all being sent information that says, okay, this area there has been covered already, so I'm not going to move in there, right? So that is essentially what's going on here. But there is no other mechanism happening here which allows them to distinguish, what's coming in from whom.
Well, I guess what they might be able to do is, if they know for a fact that they have covered this area before, and now somebody else tells them that they have covered it, they could kind of try to single out the malicious agent, right? That would maybe be an interesting thing.
Yeah, they could, and I don't think
it
absolutely. I think there are many ways that we can think about designing solutions to overcome that. So the filtering idea is one. What you're alluding to is some element of memory, which we did not include here, but we could. So arguably, the problem that we're proposing here is it's not unconceivably hard to solve. I think we could go about that, but the point of the study was actually more to show how the training paradigm or the training scheme has to be carefully thought through, because the reward function really dictates what the agents are going to do. And if you're not careful about how you design that, then bad things can happen. But yeah, I think all your ideas are valid, and that would definitely allow the robots to perform more robustly. So you can start thinking about little components that you could add to the architecture, or maybe combining some of those ideas with first principles ideas in a more hybrid approach to provide guarantees on what the agents will or will not do.
Yeah, cool. So there's definitely a lot of stuff that that might still be interesting to check out. So yeah, all the best with all that work. I'm definitely gonna check it out in the future.
Thanks.
All right. Thank you very much, Amanda, for the great talk. We see there is a lot of discussion. I'm sure the audience can reach out to you for deeper questions or...
Yeah, more than happy to follow up with anybody. Absolutely, just shoot me an email.
Great. Thank you very much. Good luck for the next steps. And
thanks,
see
JD.
you all next week for the next Autonomy Talk.
Thanks. Bye. Bye.
Thank you, Amanda.
Bye-bye.